Hello friends, welcome to another lecture of Make Mechanical Simple. Today we are going to discuss a simple topic from the subject of mechanics of solids. That is, we are going to determine the deformation of a body due to self-weight. Okay, so first of all I'll explain all the variables here. I have considered a body hanging freely under its own weight. Let L is the length of the material and A is the cross-sectional area and E is the Young's modulus, and here I have included one more variable, that is small w, and it is specific weight. Specific weight means it is the weight per unit volume. So I have taken it as capital W. Capital W is the weight of the total weight of the material, okay, divided by volume. Volume means cross-sectional area into length, total volume of the material. So small w represents the weight per unit volume. Okay, now here what you are going to do is, first of all we will consider a differential element having thickness dx at a distance x from the bottom end. We will consider a differential element having thickness dx at a distance x from the bottom end, and we are going to find the deformation of the differential element under self-weight. Then we'll extend this concept to the total volume by using integration. So this is what we are going to do in this derivation. So we have to find out what is the load acting on the differential element. Can you tell me what is the load acting on the differential element? See, I have positioned this differential element at distance x from the bottom end. That means whatever portion is below this differential element, the weight of this material will act on the differential element. Am I right? That means the weight of this portion will act on the differential. So how can we write the load acting on the differential element? That is P is equal to specific weight into volume of this portion. Specific weight into volume of this portion below the differential element. Am I right? So that is small w into volume of the, what is the volume of this portion? That is cross-sectional area into distance. So we can write it as W AX or W into AX. So this is the load acting on the differential element. Now, what is the usual deformation equation? Delta L is equal to, we have delta L is equal to PL by AE. So we can substitute the corresponding values here. What is the load acting on the differential element? The load acting on the differential element is WAX into, what is the length of the differential element? Length of the differential element means it is only dx. Dx is the length of the differential element. So we can write it as WAX into dx divided by, what is the area of the differential element? Area of differential element is nothing but A, and E is also same for the differential element. Now what you are going to do? Now we have found the deformation of the differential element under its own weight. Now we have to extend this concept to the total volume. That means we have to integrate between 0 to L to find the total deformation of the body due to self-weight. So to find the total deformation, we have to integrate this between 0 to L. So while integrating, I'll be taking out all the constants outside. So here I can cancel the areas, and taking the constants outside means W by E I am taking outside. Right, because W is a constant, that is specific weight, and E is also the constant for a material. So between 0 to L, what is remaining? X dx. Now integrating this, what we'll get? W by E is outside. Now inside bracket we have, and what is integration of x? That is x square by 2 within the limit 0 to L. So simplifying this and applying the limit, what will get? W by E L square by 2, W by E L square. If we substitute the value of small w here, that is the capital W by AL, here L gets cancelled. So I'll write the final answer here, that is capital W L by 2 AE. So this is the final equation for deformation of a body due to its own. If we observe this final equation, we can say one thing, that is, this is somewhat similar to PL by AE. See, instead of P we have capital W here and we have a 2 in the denominator. That means we can say deformation of a body due to self weight is equal to half of the deformation if the body is subjected to a direct load equal to the weight of the body. That means if we apply a W load here, capital W load here, whatever way the deformation, that will be equal to WL by AE. The deformation due to self weight will be equal to half of that. The deformation due to self weight will be equal to half of that. So I hope all of you have understood this derivation well. So if you like this lecture, please subscribe my channel and click the bell icon for further updates and share it with your friends. Thank you.